thanks everybody for joining today. Really appreciate it. Today we're going to go back to, the 1970s and look at the basics of board game AI programming. We're going to do that by looking at the way computers are programmed to play a certain class of board game. And that's the games that fit into the category of combinatorial games. So this method has applications beyond the strict definition of combinatorial games. The technology that we're going to look at today has a lot of applications, and we'll get into all of that. But I want to just start simple, and we'll start with a definition. So back in 1976, John Conway, who you may recognize that name because John Conway also invented Conway's Game of Life. He wrote a book in 1976 called On Numbers and Games. And I highly recommend it. And even if you're not a mathematician, which I am not, the games part of that book is pretty easy reading and is really interesting and offers a lot of detail. So I do recommend it. Conway and his research partners defined this class of game with the requirements that you see on the slide. So a combinatorial game in the 1976 definition has to be turn-based. Every player makes a move in turn, not simultaneously. Combinatorial games must be two-player games in the strict definition, but the principle can be applied to games with more players. A combinatorial game has perfect information. And so that means that all players have access to all the information about the game. There's nothing hidden. There are no hidden cards. There's no hidden moves, nothing like that. Everything is out in the open. And finally, there is nothing random about a combinatorial game. There's no dice. There's no shuffling of cards, no other sources of randomness. So all those criteria matter because what you're left with when you have a game that meets those criteria is a game that allows for a purely mathematical analysis. So to perform that analysis, you need to understand the possible positions in the game. So a position in Conway's definition is a legal game state. So for example, a game of chess can be understood as a series of moves that lead from the starting position to the end of the game. Every move results in a unique position. So every individual board state is its own position that can be considered. To reach new positions from the starting position, you need to understand which moves are legal. So these rules must be understood such that you can identify every possible move from every position. And finally, you have to understand how to win in order to analyze the game. The winning conditions need to be understood so that positions can be evaluated to see whether they are an endgame state or not and determine which player wins. So if you have all of those criteria in place, then the technique that we're going to talk about is going to work really well. Simple example of games that meet the definition. There are definitely more complicated combinatorial games, and tonight I'll be showing you Neutron, a game of this type that has the elaboration of having a neutral third piece available to both players that's moved separately from their regular pieces. And the techniques that we're talking about tonight can be applied to weird games like that and extended to games that don't meet the definition as well. So how do we get a computer to analyze and play these games? Conceptually, we develop a map of the possible future states of the game and identify the best possible move to make based on that look into what the future can hold. So here we have a game tree, and mathematicians use game tree diagrams to visualize this analysis. Here you can see a game tree for an almost finished game of tic-tac-toe. Every node in this tree represents a possible position or board state. There are 3 possible moves for X at the top of the tree, each of which has 2 possible responses for O, each of which leads to either an endgame position or a final move to an endgame position. So it's useful to look at a simple example like this to understand the principle. But you can start to see why we need computers for this kind of work when you consider what the full tree for a game of tic-tac-toe would look like starting with an empty board. With computer analysis, we're able to solve these type of games. So if you think about the way that a human being plays a game like tic-tac-toe, you know the rules, and you are able to think about what the other player might do in response to your move, right? Generally, when we're playing this kind of game, that's what we're trying to do. We're trying to think ahead. If I put my X here, where is she going to put her O? And so on. And if those two things happen, then what could I do next? And that's essentially what we're programming the computer to do. But unlike a person can consider things that are not fruitful and eliminate whole possibilities without having to exhaustively search your mind for what the future states would be. But computers aren't intuitive like us, and they need to walk down that whole tree in order to understand the possible future states.
So how does computer make a decision?
Right. So that's the question. So here we are extrapolating out all of the possible moves from here, but we have to. You're exactly right. We have to return back only one move that's the right next move. Okay. So actually, I won't stand up. I'm thinking about standing up. I'm already standing up. I guess I will. So here, what we've got. You see these little notations underneath the boards. Those are indications of the disposition of the game. So in this case, we've got three possible states: win, lose, and draw. And so a win is a 1, a lose is a -1, and a draw is a 0. So what you're left with when you're thinking about which move to make here, and so X has a winning move here, and X has a winning move here. So either of these two moves would be an option at this point. So at that point, when you have more than enough options, you have to decide what you're going to do with that, right? Probably make a random choice from the two equally viable options, right? Because in this case, there is nothing to differentiate those two winning moves from each other. They occur on the same turn, right? And they both have the equal value, a win. So there's in more complicated games, you might have nuances that help you determine which choice to make. But in this case, all we have to go on is win or loss. Okay. So using those tools that we've discussed already, mathematicians declare a game solved when the outcome can be predicted from any starting position. Okay, tic-tac-toe is simple enough that a person can solve it with very little experience. We kind of talked about that. But games as complex as checkers or Connect 4 are fully solved. So there's different levels of a solved game. And these are definitions that are used in combinatorial game theory. An ultra-weak solution proves whether the first player will win, lose, or draw from their initial position given perfect play by either side. Perfect play means that the player always chooses the move that leads to the best possible outcome, regardless of their opponent's moves. So that solution doesn't require any actual moves to be described, just an analysis of the game and its legal moves. A weak solution is an algorithm that can produce a win for one player or a draw for either against any possible move by the opponent from the beginning game state. So that a weak solution only works from a known beginning state. A strong solution is an algorithm that can produce perfect moves from any position, even if the play has not been perfect from the beginning of the game. Okay, and so the brute force solution that we're looking at today, and it is a purely brute force solution, produces strong solutions. I've got a slide here giving you a list of sizes of games. So tic-tac-toe, with all of its possible permutations, there's about 250,000 possible games that you can have. Checkers is a lot bigger game space. That's the term that's used to describe the possible games. Checkers has about 500 billion possibilities. Connect 4 has 4.5 trillion. Go is a number so big that we can't write it on a slide. And chess is so big that it's actually unknown. how large that game is. And that helps to understand why the brute force method is going to work better for some games than others. The more complex the game is, the more possible positions it has. And that, as you can see, can become pretty quickly unmanageably large. Like, you can trivially write a computer program to solve tic-tac-toe in real time, interactively. It's no problem. But even checkers is going to be challenging for a person using a desktop computer or whatnot. So one way to get around this is to partially solve a game. So for example, some computer chess programs use different approaches in the early part of the game. Maybe they use known openings, and they will use different methods, perhaps a board scoring tool in the mid game, but then use brute force methods to choose end game moves, because the most of the pieces are off the board. So therefore the resulting space, the game space that's left, is so small that you can play the end game that way. So it's not a one size fits all thing. And that's an example of how you can use this technique within a game that uses other tools to interact with the player. It doesn't have to be all or nothing.
So it is no AI, right?
Oh, it absolutely. I mean, what is AI? Right? AI is a marketing term coined in the 1950s to describe anything that looks like a person, right? So in some ways, it's interesting that you asked that question though, because for a long time, I would kind of stick my head up and look at what's the latest in artificial intelligence, and it was an elaboration on these methods. The big one, I think, is when you started to see these type of methods being used with memory, where a game engine could retain memory of past positions, past moves, successes, and failures. And of course, now you have neural network approaches and other approaches to games that are completely different. But these tools are still used. And one thing that's valuable, I think, about these tools is that, or this tool that we're going to talk about today, is that it's an algorithm that is really close to a lot of other really valuable and useful algorithms. Once you learn this technique, you'll find all kinds of places that you could apply it. But it's artificial intelligence, but it's certainly got nothing to do with the transformer architecture or neural networks or anything like that. This is an older generation of AI. Okay, so the algorithm that we're going to talk about today is called Minimax. And it was first theorized by John von Neumann of the von Neumann machine, back in 1928. And his formulation of it was, for every two-person zero-sum game with finitely many strategies, there exists a value V and a mixed strategy for each player, such that given player 2's strategy, the best payoff possible for player 1 is V, and given player's 1 strategy, the best possible payoff for player 2 is negative V. So he's already got the idea of numerically assigning a value to the outcome of a game. And using this idea as a starting point, the algorithm uses the tools of combinatorial game theory to evaluate the game tree and determine the available move that will lead to the best end result. The basic idea is to anticipate your opponent's best response to every possible move and select the one that minimizes the loss in that scenario. So the idea is that you're looking ahead and you want to only leave available moves for your opponent that are worse than the one that you moved. That's essentially what you're trying to do. Okay, so I have some code for you to look at. The URL is there on the screen, okay? It's spelled wrong though. That's a typo, sorry about that. It's neutron-js, and you can play it. In fact, you can play it in your browser. It's an implementation of the game Neutron. Okay, and that's a combinatorial game with an interesting twist, as I mentioned before. Besides having a pawn for each side, the game includes a neutral piece that belongs to each player, both players. So a player's move in Neutron is a two-step. Every move after the first one involves moving the neutron and then moving one of the player's own pieces. And the object of the game is to move the neutral piece to your pawn's home or to trap it so that your opponent has no moves. Yep, so there's a couple of features here that I wanted to mention. Neutron explores a pretty big game space, so it employs a couple of refinements to the basic Minimax algorithm we were talking about. One that's crucial, Neutron limits search depth. Okay, so we had that game tree, we saw that tree a couple of slides ago. What Neutron does is it stops searching at depth 3. So it can only look 3 moves ahead of the current board state, okay? So the problem with that is there may not be an endgame state 3 moves ahead. You might encounter a bunch of possible moves and there's no hard resolution. There's no winner or loser. You would have to extend the search further to figure out who the winner or loser in that scenario would be. So instead, what we do is we use an evaluation function. So when we reach a terminal state, but we're not at endgame, what we can do is then fall back to the kind of techniques that people use in games like chess, where you evaluate the state of the board and you look at all the possible moves and you score each one. So the resulting state of the board gets a score, okay? So I don't know, in chess, you might think, well, it's good to have your pawns advanced as far as possible on the board. So that might be one test that is a component of the score for the board is pawns 1 to 8, give each one a score, just give it a point for however many squares it is advanced past its starting square. That is an example of a way that you could evaluate a board for an incomplete game and still get some kind of response. It's really important to think about that distinction though. So we're moving from a deterministic solution that 100% will give you a optimal move, okay? And we're moving to a mixed solution where we're providing the optimal move as long as it's within depth 3, but otherwise we're providing our best guess as to what the optimal move would be based on our evaluation, based on the software's evaluation of the board. So the challenge that you get there is that your AI is now only as good as your evaluation. And Neutron is a pretty novel game. I've played a few hundred games of it. I have an idea of what a good board looks like from the perspective of each player, but I don't know for sure that I've got optimal strategies there. And it's interesting. So when you play Neutron, if you choose to play it, take a look at that and think about whether the machine's play becomes more predictable and more skillful as you approach the end game. And that's something that you can look at and try to tell whether this move that you just saw the machine make, is this a move that it made knowing that it's got a winning move, or is this a move that it made hoping it has a winning move?
Quick question. That evaluation, is that happening? So you're limiting the search to 3 levels.
Yeah.
Is that evaluation happening before you've even made your first move, or is it happening at the very end?
Great question. It's happening at level 3.
At level 3. Okay.
So when you, the thing that the way this algorithm works in practice is it's depth first. So it's going to hit max depth right away, right? As soon as it starts evaluation, it's going to hit its max depth, assuming there isn't a game-ending move in those first 3 moves. So it'll hit its maximum depth, and then there needs to be an evaluation of the board at that point, because there are no further moves to play. We're at the maximum depth, so we have to stop and see, what does the board look like here? What's the value of this board?
And that's where I'm a bit just a little confused, because if at that point you only have you don't have any more depth to go, so you don't know where the game's going to go.
That's right.
So what exactly are you evaluating? Just because
You're taking, so just like you would walk up to a game of chess in progress and look at the board and say, well, that person's got their queen in a great position. That's how you evaluate it.
But how do you know if the queen's in a great position if you don't know what the end state is?
Right. So I'll show you in detail my evaluation function, and we can look at that. The search algorithm also uses alpha beta pruning, which is a technique to shrink the game tree by eliminating whole branches from the search. So basically, it stops evaluating a branch if it's impossible for that branch to return a useful result. The way it does this is to keep track of the lowest identified value from the machine player's perspective and stop evaluating any tree if a lower result than the retained value is returned, because those branches would never actually be used in play. So that's another elaboration that we use in Neutron. There are other things that you can do. So just like you can prune the tree and not avoid evaluating parts of the tree that are not going to be useful, if there is a promising board state, you could double your depth in certain promising situations. That's not something that we do in Neutron, but it's certainly something that you could do, so that you're trying to balance the number of board evaluations. But if you're able to eliminate some useless ones on one side, then you could theoretically extend your search in more fruitful directions. So that's a possibility as well. We didn't implement that here, but that's a possibility. Neutron-JS, there we are. Okay, so this is what Neutron looks like. Clearly it is the cutting edge of user interface technology. But if you decide to take a look at this, the thing that you need to do is hit this Enable AI button, okay? And then we've got a little indicator here that identifies who's moving what. Okay, so the first move, nobody moves the Neutron on the first move. Once the first move is passed, then your play always starts, you move the Neutron, then you move your own piece. And the objective of the game is to get this Neutron into, in my case, I'm white, so to get the Neutron into my row. Each piece the way that it moves is it's a slide. So it moves until it hits an obstacle, either the boundary of the board or another piece. So I'll select my piece. There's my two possibilities. Okay, we'll move it up there. And there, black took a move, moved the Neutron down here, and it moved its piece there. So let's see what I can do. Now it's my turn too. Again, every move past the first move, you get to move the Neutron before you move your own piece. So if I move my piece here, makes sense, because then I'll have a winning move there, except that my opponent will have a winning move there. So the only way to safely move the Neutron here is if I can in some way block the computer player from moving its piece there. And I don't think I can. Unfortunately, I think that, how can I do it?
You move Neutron and then you move this middle piece up.
But I don't get to move the Neutron. Oh yeah, I'm moving the Neutron. Okay, so let's see. Where am I moving it? Move it here. Oh yeah, you're right. Move it there. And then we move the middle piece there, and that blocks it. Okay. All right, so we'll go here. Okay.
So what is considered a win?
There, that's a win.
Oh, okay.
And I have to move a piece. There we go, white wins. So, so you can, I played through a game, and now you have a sense of maybe some of the things that are valuable, like blocking, using these pieces to block these pieces from moving out is a really strong move, because you're really neutralizing those pieces. They're really not a factor in the game. And that means that you're blocking, like the black player is blocked from using these two spots for the Neutron. So that's what the game looks like. And if we now go to GitHub, get it right? Okay. So here is the code repository for it, but let's take a look at it in a little bit of a nicer form. So we're going to be walking through a bunch of the code, Zoom stuff. There we go. We'll be walking through the bunch of the code in the neutron.js file. That's the file that implements the game logic, the back-end logic of the game. So we'll take a look at the logic of the game. I don't know exactly how I'm going to do that yet, but we'll come up with a great approach, I'm sure. Okay. So we'll look at the code, and they're essentially there's a board object, okay? We're modeling the board. It models both the pieces and the board grid, the moves on the board. And the methods of this object provide the functionality that's required by the algorithm. That's where you find the code. Okay, so the board methods are all supporting methods, okay? So there's a lot in Neutron because Neutron is a more complicated game. In Tic-Tac-Toe, you only really need the first three. What are the possible moves? Is the game finished? And move a piece. In our case, we need a few more. We need to verify that a move is valid, okay? Because in Tic-Tac-Toe, any space that's open on the board is a valid move for either player. The moves here are not so simple, so we need to validate whether a move is allowed or not. We need to check whether a move is a winning move or not. That's actually part of our evaluation function. That's one of the ways that we cheat a little bit. We're able to check if a move is winning. Get pieces for color is a supporting function that just basically gets the array of pieces for a particular side, white, black, or neutral. Switch turn takes care of the turn logic. And that's interesting because we have a two-stage turn here. So we actually have a four-part turn order. We have player one neutron, player one piece, player two neutron, player two piece. We need to check at times whether the neutron has any valid moves because that is an endgame state. We need to get all the possible moves for a given grid. And that last one, highlight moves for X, is it indicates it's a method that highlights all the possible moves. It basically returns an array of all the possible moves on the board, but it's used in two ways. It's used on the front end to do that highlighting that you saw when you tap a piece. That yellow highlight is the result of highlight moves for X, but that also is used by the AI to understand what the possible moves are, what the possible moves for a piece are. And there is, in a couple places here, highlight moves for X and move piece. You can see the artifacts of this code used to be Objective-C for iOS. It was written for iPhone back in 2011. And those are Objective-C-like method signatures. If you've never written it, it's kind of a wacky way to describe methods. The parameters are actually interspersed into the definition. Another artifact of porting this code from Objective-C is that we have a constants file. Just sets some basic values, some constant values for us that we need. The values that indicate the different pieces and the different turns. So K white 1 and 2, K black 1 and 2 are the turn components, and the others are the first four are possible cell states.
Excuse me, what kind of language are you using?
Oh, I'm so sorry. This is JavaScript.
Okay, so
Okay.
what's the reason for using a JavaScript?
So I wrote it in Objective-C a long time ago, and that was really interesting. And it was probably This was the project where I really started to feel like I was capable as an Objective-C programmer. So that was why I did it then. And then the problem is that writing code for the App Store is kind of really developer unfriendly, because you have to pay $100 a year to be a member of the Apple developer community, and then you have to constantly churn your application to keep up with iOS updates. So they change the framework, they change stuff on the back end. You have to now make adaptations, which is a lot for a piece of code I wrote over a weekend or two. It's a lot of support obligations. So throwing it up on a web page as JavaScript allows me to share it with people without having to do any maintenance work, really, is the basic reason why. And in terms of like the language itself, JavaScript is just ubiquitous. It's I think it's valuable to use and valuable to know because you use it everywhere, right? Okay. So let's see, we've got, here's the constructor for the neutron. You can see a bunch of things that will start to look familiar based on the things we've already talked about. We have to specify the size of the grid. That's an artifact of this code actually originated, through different twists and turns. This was originally an implementation of Conway's Life. And so I've always kind of kept that same mutable grid, even though it's not really necessary for a game like this with a fixed size. We have a few tools here for the front end, whether the AI is turned on or not, which piece is selected, whether the game has been started, and so forth. Okay, let's get into those supporting methods I talked about. So we've got a whole bunch of code here. We need to here get the pieces by color, very simple method. And there's the valid move method. And what's interesting there, so basically what we're doing here is we're clearing the highlights on the grid, okay, because there's only one set of highlights that can be available at any one time. We highlight the possible moves for a given piece, okay? And then we're checking to see whether the target X and Y coordinates are in the list of valid moves that come back from the highlighted moves method. Okay.
If you don't mind.
Yeah, sure.
What's zero grid highlights do you get?
Okay, zero grid highlights basically removes all the highlights from the grid. So it's a persistent. You highlight the values and then that's persistent until they're zeroed out.
I gotcha.
Yeah. So we're moving pieces here. One key thing is skipping validation. Why am I skipping move validation at times? I'm doing that to save time and to avoid bugs in when the AI is evaluating moves. So I make the assumption that the AI is, since it's only working from a list of valid moves, it's not going to need move validation, so we skip that step here. We'll save some time. Okay, there's get moves for grid, which does what it says on the box. It gets all of the possible moves for all of the pieces. So this is both potential neutron moves and piece moves, because if you think about this specific game in terms of implementing it using the algorithm under discussion, every half move is a new position. So when we move the neutron, that's a different. We move it to position A versus position B versus position C. Each of those is a different permutation of options for the move following. So they have to be considered together. Does that make sense to everybody? Okay. So there were just a couple things I wanted to show you. So this method is testing whether the neutron can move, because that's a game ender. If your opponent can't move the neutron, you win. Okay. Okay, we talked about get moves for grid. So here's the highlight moves for X, which, if you remember the way that a piece can move, it has to slide until it hits an obstacle. So the way that highlight moves for X works, it starts from the position of that piece, and it actually just walks the grid and finds the locations where the piece will have to stop. Okay, it does that through a brute force method by checking every possible direction. Okay, and then we get our highlights from there. But this is what we really want to look at. Okay, let's see, there's evaluate moves. I'm saving all the good stuff. So we've got some, I think I've pretty much showed you all the stuff that is supporting, and then there's some like real utility stuff. Okay, so before we get into the meat of it, let's get back to our presentation, and then I'll come back for the good stuff. Okay, so then the actual Minimax implementation. First set of bullet points identifies for you what are the things that we're doing. So we are evaluating both players' moves, we are exhaustively searching the game tree, and this search is depth first. Okay, so the tools that we use here. Get best move for state is our method given a game board and a turn. Okay, whose turn is it? Get the best move for this given state, which calls evaluate moves. Okay, and evaluate moves needs state, turn, and the depth it's at, because we have a max depth. Okay, and alpha beta is our Minimax implementation, and evaluate state turn is our evaluation method. Now, one thing that I want you to notice here, we've got two methods with identical signatures, and these two methods, their code is almost identical. So when you look at this, you're going to think, well, this is like a low-hanging fruit. You should consolidate this code into one method. I spent like 2 days trying that. It's a big mistake. And it's I think it's a good reminder that don't repeat yourself as a guideline, not an iron rule. My code was way less maintainable when I tried to consolidate those two methods into one, because you just end up with a whole bunch of twisty little conditions. One of them is returning a score, and the other one is returning the best move. So they're both doing the same thing. And this is going to make a lot more sense once I've shown you how that works. And again, evaluate state turn is our evaluation method. Okay. Now that we've done that. Okay. Here we go. So, what do we do here? Get best move for state is a really small and simple method. It just calls evaluate moves, gets the list back of possible moves, right? So that's going to be the list of optimal moves. If there's more than 0, then just pick a random one from the list and return it, right? Because if they're all equally good, then it doesn't matter which one we move. There we go. Okay.
And you said that was identical to?
No, it's evaluate moves is identical. That's okay. You'll see what I mean. So this is evaluate moves, and what you're going to see is that right here. Okay. This is where we are calling alpha beta recursively. So evaluate moves is at the top end. at the very top of the call stack, it's going to call alpha beta. From there, alpha beta is going to evaluate the score for that depth, okay? So we only use evaluate moves to get the actual moves rather than to get the score. Okay, let's walk through all of this. First thing that we need to do is make sure that we are not done, right? So if we're at depth 0, we have no valid moves, okay, or the game state is finished, then we're done. We can just return. We're absolutely done. On the other hand, if the game isn't over, then we create an empty array of best moves, okay? These scores are maximums and minimums. So we are saying that if it is black's turn, right, then the best possible score initialized is -1001, because we expect to not see anything lower than -1000. And the starting best rank, if it is white's turn, is 1001, which is one better than the highest score possible. So essentially -infinity and infinity. We're checking which turn it is, okay, and then evaluating from there, what's the next turn? The next turn is basically the opposite of the current turn. So there's turns and then there's turn steps. So we have the gross turn of is it white's turn or is it black's turn, and then we have the turn stages. So then we walk through all the possible moves. We're starting here, okay? Starting here. And what we do is we apply our moves. We create a new state, applying our moves to the current state, okay? With each of those valid moves, check if it's over. If it's not over, right? If the game is not over, then we need to continue moving through the game tree. So that's what we're doing here. If the game's not done, then we're going to keep moving through the game tree, and we're going to call this method again with one lower at depth 1 lower. Okay. And then we keep track of the best move based on the score. So if the score of this move is better than the best move, right, or worse than the worst move, depending on what perspective we're looking at, then that's the new best move. Okay, does that all make sense? Okay, so now take a look at alpha beta, and what you're going to see, here's alpha beta. Just did something that I didn't want to do. There we go. There we are. Okay. So alpha beta, same signature. Looks the same, right? The difference is that alpha beta doesn't call a different method here. It calls itself. So what we want is get best move to be our where we start, because it returns moves. Alpha beta returns a number, returns a score, right? So that's the reason why we've split basically the same thing into two different methods. Does that make sense to everybody? Okay, and now the fun part. Evaluate state turn. Okay, so what do we do when we don't know how this game is going to end? Okay. Well, we know that if the y coordinate of the neutral piece, okay, if the y coordinate of the neutral piece is at the top of the grid, then white wins. And if it's at the bottom of the grid, then black wins. That's first, okay? If the neutron can't move, then it's somebody's win depending on whose turn it is. Then we've got some code here that evaluates the piece positions. So in this case, and you can see there's a whole bunch of conditional logic here. What we're doing is we're flipping the score. We're reversing the score based on whether it's the turn of black or the turn of white. So black is a positive score. I'm sorry, white is a negative score. Yeah, black is a positive score. And so what we're saying here is that if the piece, okay, the further up the grid the piece is, the better that is for you. So if you have a piece in position 4 in y-axis 4, okay, that's very, very good if you are the, now I got to do the math here, if you're the black piece, because that means you've moved a piece all the way from your home row to your opponent's and you're blocking a spot in your opponent's row. On the other hand, if you're the other player, and that means that your piece is in its original position, so that's not good, and that would be -5. So you can see the way this case statement is set up. It's set up to basically assign a 5, 3, or 1 points to each piece, depending on where it is on the board. This is just that, again, going back to that discussion we had about game strategy. That's kind of what I think is a good way to play Neutron, but I don't really know. I think there's a lot of room to make this game smarter and better. If you watched when I was playing interactively, you may have noticed that the computer actually made a completely nonsensical move. It reversed a move. You did notice that? Okay, yeah. And so remember I was saying that it gets a lot smarter when you get to the end game, because it's able to see the actual finish of the game. But before that, it's got to rely on my very untested logic about what makes for a good move or not. So that's something where there's a real opportunity for improvement. And there's also it's also an indicator, like if you're making a board game like this, you have to really understand the strategy of your game inside and out if you're going to build competent computer players. And then we evaluate this from both positions, okay, from the position of black and white. And then we're looking at the path. So what we're looking at here is, do we have a path to the, looks like it's actually just length of diagonals. Do we have diagonals available, and we're going to, it looks to me like, it's been a while since I wrote this, but it looks to me like we're going to score higher the longer diagonals that you have available to you. So those are the ways that we evaluate the board. Pretty sketchy, and there's a lot of opportunity to make this better. But what it really requires is playing a lot of games against a human, and having a conversation about the game. Like, it requires play testing. To make a better AI opponent requires play testing. The other thing that you can do when you're using board evaluation methods like this, like, let's talk about ways that you can give your AI personality, or that you can customize, you can make it intelligent or less intelligent. So for example, the way that we model easy, normal, and hard difficulty in this game is we limit or expand the number of moves ahead the game can look. So a hard game, it can look ahead 5 moves. Takes a lot longer for the game to take a turn. It takes about 10 to 15 seconds to think about its turn every time, to look 5 moves ahead. And that makes sense if we think about the way that the board, the game tree is going to kind of exponentially expand as you add more moves. And it's really sensitive in this case. It's really sensitive to even numbered max depths, because what you do when you're looking ahead an even number of moves, you're cutting out the response to the player to the next move of the AI. So it's really makes the AI very, very unreliable when you do that. So an odd number depth is the right way to go. And you can also implement personality by making these evaluations conditional, by setting up different board evaluations for different player personalities. So you might make a player that, you might make a computer player that really, really values trapping the neutron. Okay, we're going to trap the neutron. That's what this player's focus is. Or you might make another player whose personality is that it likes to move everything off of its home row. That's really important. And so there's different things that you could do in that way to extend the game a little bit. So that's the back end, and we're a little earlier than I expected. We're about 7 o'clock. So a couple other features here that I want to mention. We have, if you're going to look at this code and think about maybe implementing it yourself, we have a set of tests. Okay, the tests basically validate the basic functionality of basic functionality of Neutron, making sure that the different methods work, that the logic is sound, particularly that the AI does the right things. So those tests are there. You can look at those. They're really interesting. And there is a front end in UI.js, which, interestingly enough, so because this game is interactive, the back end doesn't actually initiate the AI's moves. The front end does, because only the front end knows whether the opponent is a computer player or a human player. So only the front end can tell the back end, we need to generate a move here. And so there is, for what it's worth, you saw the UI. There's a little user interface here that you can take a look at. And there is small amount of documentation in terms of tools to get you started, and an HTML file that presents the screen and the user interface. So let's go back to our slides and see if we've got anything else to talk about here. Looks like we don't. So I'm going to open up the floor. Oh, there's Ray waiting in the waiting room. Sorry, Ray. I have no idea how long you've been waiting, but now that we're just about finished, I'll let you in. So that's more or less what I had to share with you today, but I'm sure there's questions or comments. Anybody got something they want to share? Any questions or thoughts?
Could you go over the even versus odd number? I didn't quite
Sure.
catch the reason for that.
Yeah, I'm not 100% on that either, but let's take a look.
That's all good.
Yeah, well, I mean, let's be, this is hobby stuff, right?
Yeah.
So what I found was that when I, where are we going? When I set my max depth to an even number, what I found is that I was getting like totally nonsensical results. And in thinking about it though, if we are only looking ahead one move, okay, we're looking ahead one complete, like basically we can see the player's response. So to our move, we can see what the possible responses to our move are. So the computer, when it's able to look one move ahead, is able to avoid defeat. That's really, it's able to avoid imminent defeat. That's really all. When it can look ahead two moves, it gets no extra information because the second move is its own move. So
And it's going to evaluate at that point again anyways.
and so we get a busted evaluation. But if we go three moves, then we have that complete cycle. And again, it's looking ahead at the response from the other player. So it can plan, right? It can see what the actual response is. You really, like, unless the computer player wins on its move, looking ahead two moves doesn't tell you anything in terms of being able to determine what's a good move or not at this point in the game. So that's my best understanding, the best that I've been able to explain to myself why that code acts that way. It could very well be that I'm mistaken. So I'm always open to folks. Looks like there's just a good conversation happening in the comments. I'm always open to folks offering corrections or additional insights, but that's basically what I think is happening there.
Makes sense to me. Also, a bit of a performance gain too, because why evaluate all of these extra things if you don't need them?
Right, for sure.
Question was related to, you mentioned like the strong versus weak.
Yep,
In this case, we're only running a depth of 3.
yep,
So, but it sounded like for it to be a strong implementation, you need to know all possible outcomes.
right.
So but then I think you mentioned that this was brute force and it was strong, so.
Okay, so it's implementing that's a good distinction, and I probably wasn't clear enough in my language. So, a strongly solved game is a game where we can produce a brute force solution. So I don't know.
It's a possible thing to do.
I don't know if Neutron is solved or not. I don't know if anybody has done that work, because there's you have to actually do the work of right. So I don't know if anybody's done that, but the solution, one way that we can evaluate a strong solution is by using Minimax and exhaustively searching the game tree. So we use that technique in Neutron, but
Okay.
right. So we're using the brute force method, but we're not. We're not. Our scope of ambition is not solving the game.
It seems like it's such a nuance, because by the original definitions you gave, like needs to be 2 players, there needs to be an end state.
Yeah.
Then in thought, all games are solvable. So then aren't they all strong if you decided to go?
Well, but a
That works.
solution may not be known, right?
Okay.
If I understand it correctly,
Yeah.
the solution is not known. A game may be only weakly solved. So we know that you can win, right? We know that player 1 always wins, or can always win with perfect play, but we don't exactly know how.
Okay, so it's not an identifier of a type of game, because they're all
Right.
solved. It's just if it's been weakly solved or strongly solved
You got it.
Okay.
Yeah.
Not solved, yes.
or not solved. Okay.
Okay, I'm so glad that you asked that question.
Yeah.
So combinatorial game theory is the way that these games are described. Minimax is an algorithm that we use that exploits that theory to get results.
Okay.
Yeah, so the complexity of a game, like a typical game of any of these types, is going to be incomplete. So you're probably going to need an exponential amount of time to solve it, going like with alternating moves and all that, unless you can find a strategy that works. So this Minimax algorithm is an exponential algorithm. So
Right. So it's just
You
brute
just gotta
forcing.
Cut it off. Like,
Yeah.
And we're stopped.
Right.
development is like big business, like there's millions of dollars being spent on developing these kinds of things. And so the state of the art a little while ago was alpha beta search, but heavily optimized. Like instead of the way you're doing things, like they're doing things with matrices and matrix multiplication and heuristic pruning, and like goes on and on and on, and all the shortcuts they make to optimize it, parallel processing, multiple computers,
Very cool.
very efficient. So if you wanted to, like in Game Jam, use an alpha beta algorithm, you could definitely download exactly what you're doing, download it, and it'll be able to handle the whole problem, 5, 7 depth for this
Ooh.
game, probably.
Okay, that's really interesting.
And I wouldn't be able to tell you exactly how they do it, but it's there and you can download it.
That's super cool. So the journal article that I relied on when I started this work was from about 1976, and there has been 50 years of progress since then. And so I guess the question is, like, what I would really love to find is some concise sort of exploration of all that research to understand like where to go next. So my journey on this, I read the Conway book. I was really interested. I'm not a computer scientist. I'm a working programmer. So I got myself a book on algorithms. I started reading up on some of that stuff, learning the tools that I needed to solve this problem, and did a little bit of a literature search and went from there. But think about the amount of work for a hobby project that is.
Yes.
And then that's the challenge, right? Like, you're right, there is so much more to be done, but there's also an infinite number of other interesting things to explore out there. So this, I think, is a foundation that you can build on, that you can, it's usable if you're building your own games. Like, I think that what we've got here is usable, but there's lots of room for improvement and exploration further, for sure.
Yeah, and so if you were to download it, you still have to provide your own evaluation function because Neutron probably isn't in the engine that you would get.
Oh, well, that's a problem, because the weakest part I've got is my evaluation engine, for sure.
Yeah, but the core alpha beta search, it would just do that search faster. And
Right on.
you would be like, well, okay, instead of representing the board as, I don't know, is it an array of arrays, or is it a 25, or?
Yeah, it's a two-dimensional array.
Yeah.
So what?
They probably have ways that you code it, like, say, maybe it's a bitmask, or who knows?
Would you have a search term that I could use that I can put in the chat?
Alpha beta.
Okay, thank you, Randy. Oh, that's the search term? Okay, I'll remember that. I'm sure everyone else will. Okay, Randy suggests that Stockfish is open source. That's a pretty good place to start. So
Stockfish is a chess engine.
I will take a look there and I'll dig into that. So hopefully this has given everybody something to think about and something that you can potentially use in the Game Jam. But what we're really here to do is celebrate the Global Game Jam and prepare for it, okay? And I should have everything at my fingertips. If I was being a good hack forger, I would be able to tell you all the details about that event, but apparently I'm not. So go to hackf.org. Click on the events link on the menu, and you will be able to find out everything you need to do to register a team for the Global Game Jam and compete. And it is happening sometime in the very near future. So if you are interested in doing that, don't delay.